The theory of functions of several complex variables is the branch of mathematics dealing with complex-valued functions on the space Cn of n-tuples of complex numbers. As in complex analysis, which is the case n equals 1 but of a distinct character, these are not just any functions. They are supposed to be holomorphic or complex analytic, so that, locally speaking, they are power series in the variable z. Equivalently, as it turns out, they are locally uniform limits of polynomials, or local solutions to the n-dimensional Cauchy-Riemann equations. Historical perspective. Many examples of such functions were familiar in 19th-century mathematics. Abelian functions, theta functions, and some hypergeometric series. Naturally, also any function of one variable that depends on some complex parameter as a candidate. The Weierstrass preparation theorem would now be classed as commutative algebra. It did justify the local picture ramification that addresses the generalization of the branch points of Riemann surface theory, with work of Friedrich Hartogs, and of Kiyashioka in the 1930s. A general theory began to emerge. Others working in the area at the time were Heinrich Benker, Peter Thulin and Carl Stein. Hartogs proved some basic results, such as every isolated singularity is removable for any analytic function whenever n greater than 1. Naturally, the analogues of contour integrals will be harder to handle. When n equals 2, an integral surrounding a point should be over a three-dimensional manifold, while iterating contour integrals over two separate complex variables should come to a double integral over a two-dimensional surface. This means that the residue calculus will have to take a very different character. After 1945, important work in France, in the seminar of Henry Cartan, and Germany with Hans Grauert and Reinhold Remmert, quickly changed the picture of the theory. A number of issues were clarified, in particular that of analytic continuation. Here a major difference is evident from the one-variable theory. While for any open connected set D and C we can find a function that will nowhere continue analytically over the boundary, that cannot be said for n greater than 1. In fact, a D of that kind are rather special in nature. The natural domains of definition of functions, continued to the limit, are called Stein manifolds, and the nature was to make sheaf cohomology groups vanish. In fact, it was the need to put the work of Oka on a clearer basis that led quickly to the consistent use of sheaves for the formulation of the theory. From this point onwards, there was a foundational theory, which could be applied to analytic geometry, automorphic forms of several variables, and partial differential equations. The deformation theory of complex structures and complex manifolds was described in general terms by Kunihiko Kodera and D.C. Spencer. The celebrated paper Gaga of Sayre pinned down the crossover point from geometry analytica to geometry algebraica. C.L. Siegel was heard to complain that the new theory of functions of several complex variables had few functions in it, meaning that the special function side of the theory was subordinated to sheaves. The interest for number theory, certainly, is in specific generalizations of modular forms. The classical candidates are the Hilbert modular forms and Siegel modular forms. These days these are associated to algebraic groups, and the symplectic group, for which it happens that automorphic representations can be derived from analytic functions. In a sense this doesn't contradict Siegel. The modern theory has its own, different directions. Subsequent developments included the hyperfunction theory, and the edge of the wedge theorem, both of which had some inspiration from quantum field theory. There are a number of other fields, such as Banach algebra theory, that draw on several complex variables. Holomorphic functions. A function defined on a domain is called holomorphic if satisfies one of the following two conditions. For each point, is expressed as a power series expansion that is convergent on, which was the origin of Weierstrass analytic methods. If is continuous on, and for each variable, is holomorphic, namely, which is a generalization of the Cauchy-Riemann equations. and has the origin of Riemann's differential equation methods, is not necessary. For each index lambda, let and generalize the usual Cauchy-Riemann equation for one variable. Then we obtain let through the above equations and turn to be equivalent. To show that above two conditions are equivalent, it is easy to prove. To prove, one uses Cauchy's integral formula on the n-multiple disk for several complex variables and then estimates the coefficients of the power series expansion in. While in one variable case the Cauchy's integral formula is an integral over the circumference of a disk with some radius r. In several variables case over the surface of a multiple disk with radii s as same as the one variable case. The identity theorem holds due to the properties of Laurent series that hold in several variable case. Let be some domains simply connected, and holomorphic functions on respectively, and, if on there is then a unique holomorphic function on such that on and on. Therefore, Leopold's theorem for entire functions, and the maximal principle hold for several variables. Also, the inverse function theorem and implicit function theorem hold as in the one variable case. An example on analytic continuation. As described in the previous, there are similar results in several variables case as one variable case. However, there are very different aspects in several variable case. For example, Riemann mapping theorem, Mittag-Leffler's theorem, Weierstrass theorem, Runge's theorem and so on cannot apply to the several variables case as it is in one variable case. The following example of analytic continuation in two variables shows these differences, which was one of motivations to complex analysis in several variables. In several variables, analytic continuation is defined in the same way as in one variable case. Namely, let be open subsets in, and assume that n is a connected component if then is defined as the above is called analytic continuation of or. Note that is uniquely determined by the identity theorem but may be multi-valued. In one variable case, for any open domain there is a holomorphic function on such that cannot analytically continued beyond. That is, for any cannot be analytically continued beyond. However, in several variables case, it would occur that there are a strictly large or open domain such that all can be continued analytically too. This phenomenon is called Hartog's phenomenon, which cannot occur in one variable case. The Cn space. The simplest sign manifold is the space Cn, which consists of n-tuples of complex numbers. It can be considered as n-dimensional vector space over complex numbers, which gives its dimension to n over R. Hence, as a set, and as topological space, Cn is identical to R2n and its topological dimension is 2n. In coordinate-free language, any vector space over complex numbers may be thought of as a real vector space of twice dimensions, where a complex structure is specified with a linear operator J which defines the multiplication to the imaginary unit I. Any such space, as a real space, is oriented on the complex plane thought of as the Cartesian plane. Multiplication to a complex number W equals U plus IV has the real matrix A 2 times 2 real matrix that has the determinant likewise. If one expresses any finite-dimensional complex linear operator as a real matrix, then its determinant equals to the square of absolute value of the corresponding complex determinant. It is a non-negative number, which implies that the orientation of the space is never reversed by a complex operator. The same applies to Jacobians of holomorphic functions from Cn to Cn.